understanding polarity in terms of the molecule itself, and so we're going from trying to figure out how to figure out whether a molecule is polar using electronegativity, to actually understanding what that means in the big picture in an actual molecule. The staple remover? Okay. So when we go and figure out whether one element is more electronegative than another, so this is a representation of polarity, and this is a representation of polarity. Both of these are those trigonal pyramidal molecules, just like on the quiz today. Since fluorine is more electronegative than nitrogen is, what that means in the real world of the way the molecules behave, the electrons are spending more of their time down here at fluorine than they are at nitrogen. So by doing that, since electrons are negative, that makes the end of the molecule where the fluorines are more electronegative. They're slightly more polar than this end, kind of like a magnet is polar. A magnet has a north end and a south end. Sometimes molecules have partially positive and partially negative ends. And these symbols right here in this image, that's a partially negative symbol. And it looks like to me, the partially positive symbol didn't show up on this when it got printed. There should be a partially positive symbol up on that end, up there where nitrogen is. Okay? Partially positive. Alright? Huh? Okay. Yes, Bailey?
Why did you say it spends more time with the F than the N?
Say again?
Why did you say it spends more time with the F than the N?
Okay, let's go back to the definition of electronegativity. And that was, remember in Unit 2, we looked at the periodic table and where elements are more electronegative than others. Okay? So if we look at the periodic table with electronegativities, then we know that this end of the periodic table is more electronegative, starting with fluorine, and these are less. So what this electronegativity means, it's a relative measure of how hard an atom pulls on electrons that it's sharing with other atoms. Well, if it's pulling on those electrons more strongly, then those electrons are spending more time there. Does that make sense? It's a tug of war of sorts. Okay? So in a molecule then, if the electrons are spending more time down here, then this end of the molecule where the fluorines are is going to be slightly more negative than where the nitrogen is. Right? Does that make sense now? Okay? No, thank you for answering the question. I appreciate it. Okay? So that is the basic idea behind polarity. Now what we use is, we use this electronegativity on the periodic table of electronegativity that you have in your handout, your packet of references. We use this to calculate polar bonds and then turn around and figure out whether that means you have a polar molecule. Okay? So there's two things going on here. One is, how do you figure out if a molecule is polar? That's what we use this for. But the actual definition of polarity has to do with where the electrons are spending their time. That makes sense? Alright. So what we want to do here is take a little time and practice figuring out whether molecules are polar or not. Okay, take a little more time to do that. Now remember, you have to have two conditions to have a polar molecule. Anybody remember what those two conditions are? Uneven distribution of bonds and polar bonds. So two conditions, okay? For a molecule to be polar, no, if you did it yesterday, you're fine. I'm just making sure we're clear about it. You must have two conditions. Okay? You have to have an uneven distribution of bonds, and the bonds have to be polar. In a sense, it's kind of like our definition of, it's sort of similar to our definition, our two-part definition for, our two-part rule for significant zeros. Remember, you have to have both conditions there for it to be a significant zero in the two-part rule. Well, this is a sort of a two-part rule here too. It is a two-part rule. If you don't meet both conditions, the molecule is considered to be nonpolar. All right?
Can you repeat it one more time?
What now? Polar covalent. It wouldn't be a polar covalent bond if it weren't the only polar bonds are covalent bonds.
Okay, what was the second, like, step thing that they said?
You have to have an uneven distribution of bonds, and the bonds have to be polar. You have to have both. And so yesterday we also looked at this chart, okay, and we found that the polar range of bonds has a difference in electronegativity between 0.5 and 1.5. Okay? If it's less than 0.3, the electronegativity difference, then it's nonpolar. And then we got these ranges here where it's not so clear. We're not really sure all the time. Okay? And the reason for that are factors that go into determining polarity that are outside the scope of this class. We're not going to be getting into some more of the finer points of polarity. We're going to try to stick with the big stuff that's probably the most difficult to understand. And so once you've got this kind of solid, hopefully if you do this again in especially organic chemistry or something in college, you'll be better equipped to handle those other concepts that come into play. Anybody going into medicine, this is stuff you got to know. Okay? Any kind of medical career, yeah. Veterinarians, definitely, absolutely. Okay, nursing. This polarity stuff is stuff you need to know if you're going into anything having to do with medicine.
Even a nurse?
Even a nurse. I have tutored a significant number of nursing students in their chemistry classes. So I'm aware of the chemistry that you have to know to be a nurse. And everything depends on what level of nurse you're going to be too. You're going to have to have chemistry for all of them. You're going to have to have organic chemistry for all of them. But the depth of that organic chemistry or physical or organic chemistry will depend on the type of nursing degree you're going to get. Okay? All right. So let's figure out some polar bonds. Now, every molecule we can make, and that's every kind of combination of nonmetal. Remember, the nonmetals are those that from this stair step over to the right. Okay? Any of these over here, any of these elements over here are going to be nonmetals. And if you look on your big periodic table, that stair step is written in there for you. Okay? So any of these elements are going to be nonmetals. We can combine any of those nonmetals and come up with a molecule. Now, it might be a molecule that actually exists, or it can be just one we kind of make up to figure this out, but there's a real molecule there. I mean, we can do it for this exercise anyway. So, let's put together a silicon and a bromine. A silicon and a bromine molecule, okay? I have no idea if that actually exists or not. Okay, we're just going to do it for this exercise, okay? Well, first thing you're going to do is the same stuff we did 2 units ago when we did our electron pair shapes. Okay? We have silicon. How many dots do we put around silicon? Well, don't think. Look on your periodic table and figure it out. Yeah? It's 4 of them. Okay, so Will, do we need to go back through and figure out how? We know that? Huh? Okay, good. Anybody else need me to go back over that? All right. So, let's look at the big periodic table over here. All right. Silicon is in this column right here. Okay? What we want to do is look at all of the representative elements in that row up to that point. Okay? So I'm going to go back over here to sodium. There's the first element in that row. Okay? Sodium is going to have 1 valence electron. Magnesium is going to have 2 valence electrons. We skipped through all of the transition metals. I know there aren't any for silicon, but if you were down here, you still did the same thing. Aluminum will have 3 valence electrons. Silicon has 4. Does that make sense? Yeah, but you can't go by that all the time, especially with the transition metals and some other things that happen. Transition metals are anything in this section down here.
No, I know what they are. I'm saying, how do you know?
The thing. How many electrons?
In the transition metals?
Yeah.
Transition metals, well, that's, you have to do the orbital notation or electron configuration to figure it out probably. Because most of the transition metals are going to have 2 valence electrons to start. But, remember we got these exceptions with chromium, molybdenum, copper, and gold? Those pull one out of 1s, so those are going to have 1 valence electrons to start. Okay? And I say to start because some funky things happen sometimes. Okay? Alright, so silicon has 4 electrons. Using the same process, then tell me how many electrons bromine has. Huh? 7. Does anybody not understand that? I'll go back over that too if I need to. Everybody got that now? Alright, so bromine has 7. 1, 2, 3, 4, 5, 6. Actually, I probably shouldn't put that down there. I should put it up here. Just ignore I did that, okay? Forget that. Alright? And so I'll put a bromine over here with 7. Or you could group them first and say, well, now that bromine now has 6 electrons. But this sulfur has 5. It needs 3 more. So I need another bromine. Now the silicon has 6. The bromine has 8. The silicon needs 2 more. Bromine with 7 electrons. Now if I share these two, that bromine has 8. It's done. But the silicon has 7. It needs 1 more. So I'll put another bromine up here so that all these atoms have that octet of electrons, those 8 electrons that it wants to have. We're making a molecule. Sharing electrons is always making a molecule. Giving up electrons and gaining electrons is always ionic. Ionic bonding, okay? Alright, so now that we've got the sharing arrangement, we can go to the Lewis dot formula. In the Lewis dot formula, forget that again, I'm not having good success here today with my pen. That's why I'll try to get you guys to do it in pencil. Silicon's going to have a pair of electrons shared now between silicon and bromine. Okay, so I put a bromine here. It's going to have a silicon. This silicon here is going to share 2 electrons with bromine here. So I put that on top and put the 2 electrons in between. That's an I, by the way. Okay, silicon is going to share 2 electrons here with this bromine, and with this bromine down here, the same thing. Okay, and we've got to go around and put all the lone pairs. So these are going to be shared pairs of electrons. I still have to put in the lone pairs, the ones that aren't shared anywhere. Go back and put all those down there. So now we're into the stuff we did in the last unit. Okay, we went from electron dot formulas to sharing. That started into the last unit. For the previous unit, unit 2 was all about electron dot formulas. Now everything following that was in the last unit.